Here in chapter 7.4, we study partial fraction decomposition. What is partial fraction decomposition? Well, the goal of partial fraction decomposition is to rewrite a rational expression as the sum or difference of two or more less complex rational expressions. This process is often used in calculus for integrating rational functions. Okay, it is a skill that is used as part of an integration technique, which you will learn down the road. So, first off, what's a rational expression? You might recall from when we studied rational expressions, rational functions earlier on in the year. That simply refers to a polynomial divided by another polynomial. We have one big fraction with a polynomial on top and a polynomial on the bottom. Here I have the example 7 divided by x squared minus 14x. And what we are doing in partial fraction decomposition is taking that rational expression and breaking it apart. This particular rational expression turns into 1 over 2 times the quantity x minus 14 minus 1 over 2x. All right, so notice we take a rational expression and we are rewriting it as the sum or difference of two or more less complex rational expressions. So what we're basically trying to do here is simplify our denominators. I started off with a quadratic denominator, and notice I rewrote it as two rational expressions, each with a linear denominator. So we could check our work here by simply subtracting these two fractions. If we were to obtain a common denominator and subtract two fractions, we would get back to the original expression that we started with. So a little bit like the opposite of simplifying here. Instead of simplifying down, we are breaking this rational expression apart. So here are your steps for partial fraction decomposition. Step number 1, divide if improper. If the degree of the numerator is greater than or equal to the degree of the denominator, divide the numerator by the denominator, right? We want to complete that division if we have an improper fraction. Luckily, more often than not, we won't have to do this first step. But if the degree of the numerator is greater than or equal to the degree of the denominator, we're going to have to complete polynomial long division. Step number 2, factor the denominator. Make sure the denominator is completely factored. The form of our decomposition will be determined by those factors. Step number 3, decompose. Separate the rational expression into the sum of multiple fractions. The number of fractions will equal the total number of factors. That is very important. The number of fractions that it's going to decompose down into will equal the total number of factors. So if you have two factors, you're going to have two fractions. If you have three factors, you're going to have three fractions. If you're going to have 10 factors, you're going to have 10 fractions that it's going to break down into. The form of the decomposition will depend on whether the factors are distinct linear factors, repeated linear factors, or of the quadratic type. Step number 4, we multiply by the least common denominator, the entire equation by our least common denominator, to get rid of all of our fractions. 5, we are going to solve for each of the constants and write out our final answer. Now, steps 4 and 5 will make a little bit more sense once we get into a few examples. But right now, I just want to talk about this step number 3, the decomposition of the rational expression. So the way that your fraction is going to break apart is going to depend on the form of the denominator. A couple different forms that you should familiarize yourself with. 1, distinct linear factors. Notice here in the denominator, it factors into two factors. Each one is linear, meaning that the degree is 1, and they are distinct, right? A does not equal B, therefore they are different. Now, because there are two factors, this is going to break apart into two fractions. And anytime you have a linear factor in the denominator, that's going to generate a constant in the numerator. And so when we work with our constants, we just go in alphabetical order. This would be a divided by x minus a plus b divided by x minus b. All right, so linear factors always have a constant in the numerator. And because we have distinct linear factors, Okay, we just have a constant divided by each one of those linear factors. Here's another example of distinct linear factors, except in this case, I have three distinct linear factors. Well, again, however many factors you have, that is the number of fractions that is going to be generated. Here I have three factors. This is going to break apart into three fractions. Because each one is linear, I'm just going to put a constant in the numerator. I have a divided by my first factor, x minus a, plus b divided by my second factor, x minus b, plus c divided by my third factor. And the same thing would happen. We would just continue to tack on more fractions with more constants if we had more distinct linear factors in our denominator. We can also have repeated linear factors in the denominator. A repeated linear factor is when a linear factor occurs more than one time. So notice in the denominator here, I have x minus a quantity squared. That's the same thing as x minus a times x minus a. It is a repeated factor, meaning it occurs more than one time. It's linear still because the degree of the factor is 1. So notice, count them out. We've got two of the same factors. Well, that means it's going to break apart into two fractions. Because each factor is linear, the numerator is simply going to be a constant. However, when we have repeated linear factors, our denominators, we need to have one denominator for each time that the linear factor is repeated. So this would break apart into a over x minus a plus b over x minus a quantity squared. Okay, we have one fraction with one power for every time the factor is repeated. That means if this were a 3 here, right? If this were x minus a cubed or x minus a times x minus a times x minus a, well, again, we'd have three factors. We'd have a over x minus a plus b over x minus a squared plus c over x minus a cubed. Okay, so again, one fraction for each factor, and because they are repeated in this case, I need to have one exponent, one power for every time that it is repeated in the denominator. We can also have combinations of repeated and distinct linear factors. So all these things can be combined together. Here I have x minus a quantity squared, that is a repeated linear factor, and x minus b as a distinct linear factor. Three factors, that's going to break apart into three fractions. The first one's following our pattern for a repeated linear factor, that would be a over x minus a plus b over x minus a squared plus c over x minus b. All right, our next constant divided by our distinct linear factor. Again, notice whenever your factors are linear, the numerator is simply going to be a constant. And finally, we can have quadratic factors as well. In this case, we have a distinct linear factor, x minus a, times a quadratic factor, x squared plus bx plus c, where this factor is not factorable. Okay, so maybe we have a quadratic that is completely factored already. Okay, leaving us with a quadratic factor. The difference with quadratic factors is that your numerator changes. Instead of just being a constant in the numerator, you're going to have a constant times x plus the next constant. Okay, your numerator is actually going to be linear. This would leave us with a over x minus a plus bx plus c divided by x squared plus bx plus c. So again, if you have a quadratic factor, your numerator of the fraction above that quadratic factor will be linear. Constant times x plus the next constant. So let's look at a couple examples here of decomposing rational expressions, all right? Write the form of the partial fraction decomposition of the rational expression. Do not solve for the constants, all right? So we're not solving them out just yet. I want to make sure you guys understand the different forms. Well, the first step, if we don't have to divide, which we don't here, is to factor the denominator. And in this case, our rational expression, the denominator factors into x plus 1 times x plus 3. And so notice in the denominator, we have two factors. Each is linear and they are distinct. Linear factors decompose into a constant over that linear factor. And because they are distinct, two of them, I'm going to have two fractions, a over x plus 1 plus b over x plus 3. Again, constant divided by the first factor plus constant over our next factor. Let's look at another one here. X squared minus 3x plus 2 divided by 4x cubed plus 11x squared. Well, again, we begin by factoring our denominator. This leaves us with an x squared times a 4x plus 11. Here, I have a repeated linear factor. Notice that x squared means x times x. That's a repeated linear factor and a distinct linear factor. Well, when we have repeated linear factors, the numerators are still going to be constants. However, our denominators, we need to have one power for each time it is repeated. So my first fraction would be a divided by x plus b divided by x squared. Again, I have one fraction for each time it is repeated, and I have one denominator for each time it is repeated as well. This is the first power, and this is the second power. There's my repeated linear factor plus c, a constant, divided by 4x plus 11. There is our distinct linear factor on the end. Okay, x cubed plus 2x squared plus x plus 1 divided by x plus 2 to the fourth power. All right, this is already factored for us here, and we have a repeated linear factor, except in this case, this one is repeated 4 times. Because it's repeated 4 times, we are going to have 4 fractions. Because they're linear, each numerator is going to be a constant, and because it's repeated linear, I need to have one denominator representing each power for which it is repeated. This would break down into a over x plus 2 plus b over x plus 2 quantity squared plus c over x plus 2 cubed plus d divided by x plus 2 to the fourth power. Again, one fraction for every factor, right? It's repeated 4 times, so I have 4 fractions. It's linear, so each one of my numerators is a constant, and I have one power for each time it is repeated. All right, let's look at another one. X squared minus 5x plus 6 divided by 2x cubed plus 8x. Here we can again begin by factoring the denominator. Our greatest common factor is a 2x. This turns into x squared minus 5x plus 6 divided by 2x times x squared plus 4. This is now completely factored. 2x would be a linear factor, and x squared plus 4 is a quadratic factor. So because we have a linear factor, this would break down into a over 2x plus quadratic factors always break down into a linear numerator. That would be bx plus c over x squared plus 4. A over 2x plus bx plus c over x squared plus 4. And here I have x cubed plus x squared minus 3x minus 3 divided by 3x plus 1 squared times the quantity x squared plus 3x minus 1. Now in this denominator, 3x plus 1, that is a linear factor. It is repeated twice. And here, x squared plus 3x minus 1. Well, this is not factorable. So this factor here is actually a quadratic factor. So we have repeated linear and quadratic factors. Again, 3 factors in total, this one happening twice, this one happening once. It's going to break down into 3 different fractions. The first one being a over our first linear factor plus b over our first linear factor squared. Again, with repeated linear factors, we have a denominator for each power for which it is repeated, plus cx plus d over x squared plus 3x plus 1. Whenever we are dealing with a quadratic factor, our numerator is going to be linear constant times x plus the next constant. So there are a bunch of different forms of partial fraction decomposition. In the next video, we are going to go through and talk about the next step, which is solving for each one of these constants.